Hello, let's talk about probabilities today. So, very important topic, probability theory. The foundations of probability in the simplest possible model is as follows. You have a set, or we usually use the Greek letter capital omega, which means the sample space. The sample space contains everything that could happen, all states of the world that could happen. We do not know which state is going to be the true state. So we have points inside of a set. A subset, like A or B, is called an event. Okay, so an event is just any subset of the sample space. In more advanced probability, they require sigma algebra. Complications, that doesn't matter. Here is very simple. Just think of an event as any subset of your sample space. Okay? And a probability, it's going to be a function mapping events into numbers between 0 and 1. Okay, in the interval 0 and 1. So every probability has to be at least 0 and at most 1, okay, of any event. But it has to satisfy axioms. The first axiom is that the probability of the entire sample space must be 1, okay? The chance of finding anything is 100%. And if the two events, E1 and E2, two subsets of the sample space, they have no point in common, we call them disjoint or mutually exclusive events in this case. They have no common point, okay? Then the probability of being in the union is the sum of the probabilities of being in event E1 plus the probability of event E2, okay? But this is an important condition. Now let's see a couple of properties. Suppose the event E1 is the whole sample space and event E2 is the empty. So what we have? Well, the probability of E1 union E2, it's going to be the probability of the sample space is the probability of the sample space union the empty set. But this is equal to 1 because of this first axiom. This, I did nothing. I just take the union with the empty set, which is not changing the set. And now I know the intersection of the sample space with the empty set is empty. The intersection of the empty set with any set is the empty set. Okay? So I can use this second property to say that's probability of this plus probability of the empty set, which is, this is 1 by this first axiom. The probability of the empty set is that. So 1 equals 1 plus the probability of the empty set, which means the probability of the empty set has to be 0. Okay? And in general, if you have two events, A and its complement, the complement is all the points that do not belong to set A, right? If you do the similar calculation, you will show that they will end up to 1, because the union of these two is the whole sample space, which has probability 1, and there is no common point between a set and its complement by definition, okay? So this is true. So the probability of any complement is just going to be 1 minus the probability of the event, okay? So the probability of any event plus the probability of its complement is always 100%. So if an event has probability 20%, its complement has 80%. 0.2 and 0.8. Now in blue here, another property, the probability of union of three events, E1, E2, and E3, it's the sum of their probabilities provided if the intersections of these events 2 by 2 are empty, if they don't have any intersection 2 by 2. And to prove that, I can use this property twice. I think of this E2 as the union of E2 and E3. So if the three properties are satisfied, then the intersection of this union here of E2 and E3 with E1 is empty. Okay? So these two properties here imply that. And then I can write like property of E1 plus the probability of E1 plus the probability of the union of E2 and E3. And now from here to here, again, I use this and this property here to say that the probability of E2 union E3 is the probability of E2 plus the probability of E3. Okay? So I started here, I move, I go to this, and I get to that. So in general, you can do that many times, any finite number of times. If you have infinitely many sets, then it's more advanced. I will not cover today. We talk about sigma algebra, sigma additivity, and so on and so forth. But as long as the events are 2 by 2 mutually exclusive, the probability of the unions is the sum of probabilities. Now, things are different if the events have some points in common. Let me show you. Okay? So in this diagram, I have a sample space. I have a set A, an event A, and an event B. So in red, I have points that belong to A but not to B. In blue, the points that belong to B but not to A. And here in the middle, the intersection in green. Okay? And I write, and these are three different parts of the union. So the probability of the union is the probability of the elements that belong to A but do not belong to B. And that's the notation for the events that belong to A but not to B. In blue here, the states that belong to set B but not to A. And in green, the points that belong to both A and B. Like in the picture here. In red, those points of the sample space that belong to A but not B. In blue, the points of the sample space that belong to B but not A. And in green, in the middle, the points that belong to both A and B at the same time. Okay? Now, here I copy. On my left-hand side, I copy. And what I do here is I write probability of A minus B. This red is this bit here. I add the probability of the intersection, which is the green. Then I have this blue here. Then I add and subtract this term here, the probability of A intersection B plus and minus itself. I add and subtract the same thing, so I'm not changing the equality. And now I apply this property here to say that the probability of the points that belong to A but not B plus the probability of the points that belong to A and B, well, that's just the probability of the points belonging to A. Because the intersection here is empty, right? Either the point is in the red region or in the green region. It cannot be on both at the same time. There's no common point between the green and the red regions, okay? So this is just the probability of A. This part here, the probability of B minus A plus the probability of A intersection B, is exactly the probability of B, again by this property here. Points are in the blue region or the green region are the points of set B, of event B. Okay? So the probability of A union B is always the probability of A plus the probability of B minus the probability of the intersection. Okay? Here, the intersection is empty. I would have to subtract the probability minus the probability of the intersection. But the intersection is empty and the probability of the empty set is 0. So I don't have to put the 0, right? In general, we don't have to put the 0. Add 0 to an expression will not change its value. Okay, good. Now let's see this example. A biased coin. You flip a biased coin, it could be heads or tails, but the probability of being heads is 60%, 0.6. The probability of being tails, 0.4. The probability of nothing is 0, and the probability of getting something is 1. So that's the simplest possible example, a state space, a sample space with two outcomes, heads or tails, and four possible subsets of this set with these probabilities. And these numbers will satisfy all the properties that we have. Okay? Hope this is a good start for your study of probability theory. See you next time. Bye bye.